Okay, hello everyone. Welcome to today's CGD seminar. Today we have Dr. Christopher Little as our speaker. Chris is a serious visiting fellow in CU Boulder in the Department of Atmospheric and Oceanic Sciences. And this will be and his visit will end till the end of this month, right? So when he's not in Boulder, Chris is a physical oceanographer and a senior staff scientist at Atmospheric and Environmental Research, that is AER. His research seeks to improve the understanding of physical controls on the rate of sea level change, mainly focusing on the coupled ocean ice sheet interactions and the relationship between basin scale sea level change and those occurring at coastlines. Chris also developed some approaches to translate improved understanding into predictive models useful for scientific analysis and risk assessments. He received his PhD from Princeton University and bachelor degree in chemistry from Williams College. I, I think that's a pretty good bio. Without further ado, let us welcome Chris to give us a talk about the coastal sea level observations. Thank you so much. Thank you.
Okay. Is this working?
Yes, I think so.
Great. Okay. Well, thank you very much. And thanks, everybody, for being here today. I have been enjoying my time here in Boulder since roughly June, and definitely interacting with people both at CU Boulder and also at NCAR, both in the lab and then on trails every once in a while. It's been a really wonderful time, but I did want to have the opportunity, at least before I went back home, to give a talk in person. And I hope that over the next 2 weeks, it can lead to some follow-up discussions while I'm here. And if it doesn't, for any reason, this is my info, and you know where to reach me. And of course, everybody remote, you can reach me via email. Okay, so today's outline, I'm going to give a little bit of background on coastal sea level variability in terms of its importance, as well as how we measure it with tide gauges and what those tide gauges measure. And then I'm going to talk about some interesting aspects of decadal variability that we see in the tide gauge record. And this is really coming from a couple of recent papers looking both at the US East Coast, which is where I will start, or the North American East Coast, and then sort of expanding to see some coastal variability that seems coherent with that in other regions of the globe. So I haven't had a lot of time in order to answer all those questions about the decadal variability that we see in observations. Indeed, that was really the goal of this sabbatical. So I'm just getting started. But I think I've unearthed some sort of promising ways in which we can use models to answer at least a subset of the questions that are coming out of the sea level record. And so I'm going to talk a little bit more about a strategy for how I'm going to answer those questions, and then some early promising results, at least I think they're promising, that hopefully we can capitalize on going forward and others can contribute to. And I'll talk a little bit more about that in terms of these case studies. So these are examples of where I'm starting to look at models as tools that we can interpret this coastal sea level record using, and the development of diagnostics that allow us to see whether the models are doing a good job. Okay, so as background, coastal sea level has importance to both society at large as well as the scientific community. There are long-term global changes going on in sea level, rise almost everywhere, and this is going to lead over time to inundation of infrastructure, cultural resources, coastal communities, and this is an important topic, one that deserves a lot more research into, and that I spend some of my time working on. But there's also variability that occurs in sea level over many different timescales. And these all act to modulate the frequency and severity of coastal floods. And the sea level varies, locally in a way that can be completely different from what's happening at a global level. So if we look at the figure off to the left-hand side, this is a plot of flood days in Norfolk, Virginia, from 1928 to 2018. And you can see that there is a steady increase in the amount of flood days, but that there's substantial amounts of variability on a year-to-year basis or even on a decadal basis in these flood days, which is relating to this variability in sea level. So one of the sort of timescales that I'm going to be focusing on in the rest of the talk are sort of these interannual to decadal fluctuations in sea level, which can have an influence on flood days. And the amplitude of these are actually relatively large. They can be 5 to 10 centimeters, which is the equivalent of several decades of global mean sea level change. They also have a large spatial extent. It's not just affecting flooding in one location. It could be affecting flooding all up and down a coastline. And then finally, they might be predictable. And so we might have the ability to do something about forecasts of the sea level variability if we understand the mechanisms better that we see in the tide gauge record. Okay, so I'm putting another element of the importance, and I'm saying that this is mostly about science, but it also influences society as well. So tide gauges are a relatively simple measurement where you measure the height of the sea surface relative to land. And they've been used for a long time in many locations globally to help with navigation. You need to know whether the water is sufficient to take your boat into a harbor. But kind of as a side effect, we've got measurements that are very stable and very long-term in a lot of places globally. So if we look at the tide gauge distribution on this map to the lower left, we can see that there are many locations, albeit primarily in the Northern Hemisphere, where we have tide gauge records that go back 60 years, that's sort of in yellow, but long tide gauge records over many coastlines. And those long records are kind of unique in terms of stable instrumental records that we can understand climate variability and sea level variability. You can resolve decadal fluctuations in sea level. You can see modulations of those lower frequency variability. And you can go back to sort of pre-anthropogenic sea level rise. So you can actually see a signal of a change where the rate of sea level rise has accelerated greatly. So I think these are incredibly valuable tools in order to interpret what's happened in the past. So some of the uses that these tide gauge records have is obviously we can reconstruct using them global mean sea level change as well as differences in sea level changes between different basins. We can also use them to try to infer what's happened at a regional level with respect to climate or ocean circulation, and that's a topic that we'll touch on more in this talk today. And then finally, we can kind of do, so I should say, in understanding regional and ocean climate variability, we need tools in order to relate what we're seeing in sea level to the ocean circulation and to climate variability, which is sort of the first part of this talk, how models can help us interpret what we see in these coastal records. And then they also have utility in evaluating models at the coast where it matters for society and over long time scales, right? So these are, we can start to look at low frequency variability and whether the models are doing a reasonable job of capturing that low frequency variability in coastal sea level that might be related to low frequency variability in climate. So we can also use these observations as a way to go back and assess whether the models are doing a good job. So in that sense, I think they're a unique resource. All right, so what I mentioned in the previous slide was that tide gauges are a relatively simple measurement and a stable measurement. And that's true. But they measure sea surface height relative to land. And what that means is that they record what's called relative sea level. And so the simplicity in the measurement actually becomes a little bit more complicated when you have to interpret what those tide gauges are actually seeing, because there are many different processes which influence coastal sea level. Some related to climate, some not related to climate, some related to climate in the present day, some related to climate in the past. So we need to understand that all of these factors are going into that tide gauge record. So we can kind of lump these factors or components of sea level change into those that are driven by ocean atmosphere dynamics. So wind stress moves water around, piles up the ocean in particular locations. Density changes, you can heat or cool the ocean, and that's going to affect the height of the water column or the sea surface height. Those are the types of factors that, at least in today's talk, I'm going to be trying to isolate or pay attention to in the sea level record. But there are other things which influence sea level and relative sea level in particular at a local level, such as mass exchanges from the ice sheets, from glaciers, from terrestrial water sources, from damming and irrigation practices. All of those can influence how much mass or water is contained in the ocean. And they also have unique local fingerprints, which can appear in coastal sea level records. And then finally, you've got adjustment of the land, vertical land motion, due to potentially climate-induced glacial isostatic rebound. But you can also have local factors which influence subsidence, like groundwater extraction or hydrocarbon extraction. So all these things do show up in the tide gauge sea level record, and if you're trying to interpret the tide gauge sea level record, you need to figure out a way to get them out of there. So I'm not going to go into that much detail in how we correct the tide gauges in order to isolate the ocean circulation signal. What we really want to do is we want to get a quantity called dynamic sea level out of the tide gauge record. And that's the sea surface height relative to the geoid with the inverse barometer correction removed. So in order to do that, some standard techniques that we use are trying to remove vertical land motion. Now that can be done over the more recent past by having a co-located GPS so you can see the land motion. But that gets more difficult as you get further back in time. You can use GIA models. You can also do something simple like linearly detrending the tide gauge records. You can also, using reanalysis products, remove surface pressure, which takes out the inverse barometer effect. And then you can do more detailed analyses in order to deal with things like the fingerprints from mass exchanges between ice and the ocean. Another thing that you can do, which is simpler, is you assume that some of these corrections are small relative to the local dynamic sea level variations over the timescale of interest. So I'm not going to get into details, but I just want to make the point that if you're going to use tide gauges as a record of ocean circulation, you have to be careful into what processes you're taking into account. Okay, so if we do that, and we look at a sample tide gauge record from New York City that's just linearly detrended and then the inverse barometer correction removed, we can see that the thin black line has a lot of variability in the annual mean, and then we can also see variability that appears at longer timescales with that smooth time series. Once we do those corrections and we have this record of dynamic sea level, then we can start to think about, well, what does that mean in terms of the ocean and climate variability that's occurred in the past? And I should also mention that when we do this correction, it's very similar to what we have to do when we're comparing ocean models or climate models, because some of those climate models don't have the processes that are all the processes that are influencing tide gauge sea level. So these corrections, both to interpret the past and also to compare with models, we have to do similar things.
What are the units in the vertical axis in that graph?
Oh, so that's centimeters. Yeah, sorry about that, left out. Okay, so that's the background for today. I want to talk a little bit more about some of these features that we're seeing in the tide gauge records in the two papers which I mentioned earlier. Again, it's going to be a condensed presentation. Those papers are out, and there's more detail in there. All right, so if we look at the time series that were analyzed in this 2021 paper, we looked at 29 tide gauges with a record between 1950 and 2019. We want them to be complete on a monthly level, at a monthly basis, and then we annually average and linearly detrend the tide gauges after the inverse barometer correction. So it's a very busy slide, but looking from the bottom of the left to the top of the right, we're going from south to north along the North American East Coast. And you can see a lot of variability at the annual mean timescale, and then also when you smooth it out. And I don't obviously want us to capture every detail in this slide, but what you can see in a lot of places is common variability along stretches of coastline. So for instance, if you look at the Gulf of Mexico and southeast US, you can see an increase in sort of the 2012 period, which has been talked about recently in the press and in recent papers. So there is this sort of regional scale signal, which gives us a little bit of confidence that it's not just a tide gauge recording something local, but that there's actually something going on at a regional level. So the things that I'm going to be focusing on today, at least in the US East Coast time series, are these sort of decadal timescale bumps, which appear post-1960. They don't appear, but they're much larger in amplitude along the northeast US coast. And you also see something with the same sort of frequency in the southeast US, potentially at a slightly earlier time in the 20th century. So that's variability that we're looking at. So the goal in the paper, in this analysis, was to more rigorously look at some of the spatiotemporal structure along the US East Coast in this sort of decadal band. So what we did was use wavelets, wavelet power and coherence in order to understand how this time-varying decadal variability manifests along the coastline. So if we do a wavelet power spectrum on the annual mean New York City detrended sea level, you can see that there is this very prominent band appearing sort of in the 1960 to 1970 timeframe at about 12-year periods, so we can say maybe 10 to 15-year periods, where all of a sudden you start seeing higher power in that time series. It's evident in the time series, but the wavelets give us a little bit more rigorous way to look at that. So if we take that 12.4-year period and we look at all the tide gauges along the coastline from the Gulf of Mexico all the way up to Canada, we can see that in most of the tide gauges, there is this band of enhanced variability that occurs in the mid to late 20th century, and that it's significant relative to red noise, which was our significant testing we deployed. If we look at the sea level power, this is exactly the same plot as what I was showing before. We can see that, again, all these locations, with the exception of a few, show enhanced variability over this time period. If we look a little bit more deeply, it seems like that north of Cape Hatteras, so north of North Carolina area, starts a little bit later in terms of that decadal variability, although we didn't do any statistical testing in order to compare the time at which this decadal variability emerged. If we take this 12.4-year period and instead of looking at the power in the time series, we look at the coherence relative to Charleston, South Carolina. So this is looking, again, only at that 12.5-year period, and then looking at how well correlated at that period the time series are. And you go south or down from Charleston, we see that most of those tide gauges south of Charleston at that frequency band are correlated and they're in phase with Charleston. But we also see this appearance north of Cape Hatteras of that same of a coherent signal north of Cape Hatteras, and mainly over this 1960 to 1990 period. So there's something that's happening all along the US East Coast over that period of time that's sort of a common mode of amplified decadal variability. Okay, so I'm going to take a little bit of step back from that just to think about some of the implications of this. So the conventional wisdom along the US East Coast is that sea level north of Cape Hatteras is not correlated with sea level south of Cape Hatteras. And so a lot of that information comes from altimetry and tide gauge records over that same period, say 1993 to the present day, 1993 being when the altimetry record started. So this is supported, if you look at the altimetry figure off to the left side, by a high correlation in the annual mean over the northeast US shelf, extending into Canada, with sea level offshore of Cape Cod. So all of the shelf sea is going up and down at the same time north of Cape Hatteras. And then if you look south, that correlation disappears. And that's varying independently. And if we instead look at the tide gauge record and we look at the cross correlation, we can see that the tide gauge's correlation is really strongly segregated into two groups, north of Cape Hatteras and south of Cape Hatteras over that time period. But if we look further back in the tide gauge record to this period of amplified decadal variability, we can see a much different cross-correlation structure in which almost all the coast is dominated by this sort of common variability, and there's not this distinction. So this has implications in terms of what we think of as driving coastal sea level variability on the US East Coast. It may not be separate between north and south. It may instead vary depending on this sort of epoch or period of time that you're in between a common mode and one that's disconnected. So when we look at altimetry records and try to interpret what's going on with the circulation, I think we should keep that in the back of our minds, that might be something that's more of a function of the time period which we've sampled. And then, of course, if we're using indices to reconstruct climate, we should take into account that those indices may mean different things at different periods of time. Okay, so that's just a little aside to think about some of these implications. The next analysis that I worked on in this 2023 paper was looking at whether this signal that we see on the east coast of North America exists elsewhere. So in order to do that, we wanted to look at both the period in which you don't see this variability, which is back pre-1950, 1960, and also this period of amplified variability. So it meant that I had to restrict the set of tide gauges that I'm looking at. So obviously this is sort of a very inhomogeneous sampling of global sea level, but it's more a function of the fact that I wanted to look at the longest records possible. So when we do the same sort of analysis and we look at the power around 1980 in coastal sea level in these tide gauges, if we look at the US East Coast, we can see that there's high power and it's significant. But you can also see high power along the west coast of the North American continent as well, starting at Panama and then extending all the way up to the northwestern United States. You also, I know it's tough to see, but there is a point at Sydney where we have a record, and that also shows this coherent variability or this high power in the variability. You don't see this signal in Europe at all. So extending this result to look at this 12.4-year period frequency band, we're looking at the same sort of analysis where I'm looking at the coherence between different tide gauges. And this time I'm looking at the coherence of different tide gauges, 64 different tide gauges with the New York City tide gauge. So New York has a coherence of 1. I'm sorry for the lack of a scale on this. And you can see that most of the tide gauges on the eastern US coastline are coherent, and this is most of the northeastern US coastline, are coherent with that signal. But you also see that those places where we saw the enhanced power in the Northeast Pacific and in Sydney also are coherent with this New York City tide gauge sea level record. So it brings up the question, well, what is the relationship between these two ocean basins? One way in which we can start to learn a little bit more about that relationship is by looking at the phase of the relationship. So how, whether there are lags between sea level on one coast versus the other. And so what the plot on the left shows is that in these northeastern US tide gauge records, the signal is very coherent and in phase. There's no real differences there. But then if we look to the sea level on the western North American coastline, we see that that actually leads during this period of coherence what we see on the East Coast. And if we apply that to Sydney, we can see that Sydney actually lags by 4 years, which actually means that what's happening on the eastern side of the Pacific Basin is out of phase with what's happening on the western, assuming that we can trust what we see in the Sydney record. Okay, so that's sort of setting the stage, and those are really the essence of the sabbatical, is to try to answer some of the questions that those sea level records bring up. So I think that we need to use models in order to do that. I think it'd be very difficult to do this solely through observations and reanalyses. That being said, in this 2023 paper, I did do some analyses, statistical relationships between coastal sea level and reanalysis atmospheric data. What that allowed me to do was come up with some generic hypothesized mechanism for why we're getting the sea level variability and why it's coherent and why it's enhanced. But I'm presenting this purely as like a hypothesized mechanistic pathway, and I think that what we need to do is really answer the questions that it brings up. That being said, I think that being said, that's a funny phrase. I think I saw a Larry David bit about that. Anyway, so I think that gives us a good basis to start to explore some of the mechanisms, start to divide up some of the questions. So I will present that now. One of the things that jumped out of this statistical analysis is that we saw coherence with SSTs and coastal sea level in the central tropical Pacific. Coherence with both SSTs and winds at this frequency band. So the mechanism that might lead to is an equatorial trapped, similar to what we see over ENSO type timescales, is an equatorial trapped sea level signal that propagates eastward and then continues up the coastline. So you would associate that high SST signal and that zonal wind, westerly zonal winds, to lead to higher sea level on the west coast. Now, SSTs have also been linked to, via stationary Rossby wave response in the atmosphere, to surface pressure variability. So we did the statistical analyses with sea level pressure, and you could see that there was this evidence for a low off the coast of California and a high off the coast of Greenland. Now that low would be associated with a circulation that would drive an increase in sea level, given the alongshore winds, a relaxation in the upwelling regime. And that high is a little bit more complicated and sort of centered in the Labrador Sea region, but it results in a relaxation of the winds, and you also see an increase in the SSTs in that area. So if we do the coherence analyses on reanalysis heat fluxes, what it actually shows us is that that high pressure is associated with reduced heat loss in the Labrador Sea. And then we can think about that as creating negative density anomalies in the Labrador Sea, an increase in the steric height, and then what that does is propagate along the US East Coast and lead to coastal sea level variability, a high that's lagged, associated with that lag between the Labrador Sea and the coastline. So dwelled a little bit too much on this, but the idea is that these are sort of the schematic hypotheses that we can then explore if we start to break up these questions using different models. I should mention there's also questions about whether that Central Pacific SST is in fact the origin of this or whether it's linked to other tropical basins. And then another thing that I didn't explore was that this modulation of this decadal variability, it appears to be timed pretty closely to AMV phases. So that was the only sort of speculation that I brought up along those lines. All right, so these questions are really, or these observations really raise a bunch of different questions. So I can kind of break these up into what processes drive decadal sea level variability in the Atlantic. Can we nail down a little bit better what the forcing is that's associated with that sea level variability on the East Coast? And why is it common along the East Coast? We could also think about questions relating to what processes drive decadal sea level variability in other basins, like the Pacific. We can think about, is it really that tropical signal that's driving the Pacific SSH variability, or is it more the alongshore winds? As I alluded to before, there's questions about the nature of the teleconnections and the interbasin interactions. And then sort of riding on top of this is, what's going on so that we're seeing the modulation over this 30 or 40-year period in decadal sea level variability. So they're all questions that I'd like to pursue. I'm just trying to figure out how to break them up. And of course, I'd love feedback along those lines. So now we get to the part where I talk about more of a general strategy and give some examples of how I'm trying to approach some of these problems using existing and new simulations. So the way I see this is that I've got this set of research questions that are out there having to do with coastal sea level variability. And a set of available simulations. They vary in the way that they're forced, the number of models that we use, their horizontal resolution. And the process is really one of matching the right simulation to answer the types of questions that we're looking for, looking to get at. And I meant to say that one of the reasons why we need to do this is because we're really asking a lot of the models. We're trying to represent low frequency variability in climate and the ocean, and also represent their impact on the coast. So it might take an interesting, selective and sort of hybrid of different types of modeling approaches in order to answer these questions. So the way I see this going is we try to create appropriate diagnostics that reflect the variability that in coastal sea level that we're looking to understand. That could be time and spatial scale of those metrics, but I'm also going to give a couple examples of other potential diagnostics and other potential ways we might think about matching models and observations. This gives us the opportunity to say, no, the model is insufficient. Then we have to kind of iterate and go back to what set of models, what set of questions they're looking at. But if we find that a model, or a set of simulations can give us some information or can match the observations in a reasonable way, then we can use those in order to probe some of the mechanisms that are at play. And then hopefully, fingers crossed, get some answers to these questions that I've kind of stirred up. So just get back to the title of the presentation, right? We're using these diagnostics. If we find that they do a good job, then we can use the models to inform our interpretation of the sea level record. If they don't, then the observations have informed that our models are not right for this task. Okay, so I think I've got about 10 more minutes, and I can give a couple of quick run-throughs on some case studies of applying these diagnostics to particular aspects of the questions that are stirred up from the tide gauge sea level record. Again, mostly they're partially fleshed out, but I do think that there's some promise here. Okay, so the first case study that I'm going to talk about is this question of what's driving decadal sea level variability in the Pacific. And do we have models that can help us understand that, given that match up with what we see in the coastal sea level record? And if they can help us with coastal sea level, maybe they can help us understand other problems relating to that decadal variability, tropical Pacific decadal variability. Before we get there, what we need to do is try to create some diagnostics of the observations of the coastal sea level record in order to test our models with. So what I've done is, instead of looking at that full 1930 to present period, I've limited the number of tide gauges that I'm looking at here to 1958 to 2018. So just during this period of relatively enhanced decadal variability. And when we look at the tide gauge records that we have more, which can give us a better idea of what that spatial structure is in the coastal sea level record. So if we take those tide gauges and look at an EOF of the first EOF of the 5-year smooth time series, what it gives us back is sort of this east-west dipole in structure, which kind of fleshes out what we saw in the Sydney record, which was just one location on the western side of the Pacific Basin. And we also recover this decadal variability in the tide gauge record, which is reassuring. And we also note that there's sort of a decreasing trend, which means decreasing sea level on the western side of the basin, increasing on the right, which matches up with what we see in altimetry, where we've seen this sort of dipole over the more recent past. So it seems like there's a lot of interesting things that we could discuss about the EOF in the tide gauge observations, but you can also apply it to models to see whether they're representing this variability. So what I've done here is look at 2 CESM forced ocean sea ice simulations, so ocean-only simulations, meant to represent that same period of time at low resolution and at high resolution. And I run the same sort of EOF analysis on it. So if we look at the principal component time series, we can see that the models, when they're forced with a reanalysis atmosphere, do a good job of representing that decadal variability in the trend. But if we look a little bit more about into the spatial structure, we see that on the eastern side of the basin, the LR and the HR give sort of a comparable amplitude of sea level variability. But if we start to look at the western side of the basin, we can see that there is a little bit more damped variability, and it's damped in this EOF, which means that either it's damped or maybe it's incoherent with what's going on the eastern basin. So point is that we apply this diagnostic and we can start to tease out, which might be, where and what simulations might we be able to use in order to understand some of the sea level dynamics and the ocean dynamics that are underlying this decadal variability. Perhaps we might be a little more cautious of what's going on the eastern side of the basin, in the western side of the basin than the eastern side, but more work will help clarify that. Okay, so another case study has to do with this question of modulation. So the timescales associated with this modulation are like 40, 50, 60 years that we see in the observations, which make it difficult to have either forced ocean-only simulations or historical simulations that can actually capture that variability and we can generate statistics from it. But one thing that we can do is look to long pre-industrial control runs and try to understand and make the assumption that this variability that we see in the common mode along the US East Coast is internally driven. And if we can see that matches up with our observations in terms of the amplitude, periodicity, or the modulation, then we might be able to understand a little bit more about the dynamics that are underlying that variability as well as its modulation. So I'm switching gears here and working with a NOAA model in CM4, and I'm showing a time series of the bandpass filtered US East Coast sea level time series that does show similar amplitude variability to what we saw in the observations and this sort of multi-decadal modulation in that time series. So we can look at that both with respect to the actual time series, the bandpass filtered time series, or we can look at the amplitude of the power in that time series. Is it enhanced or is it damped during this time period? So if we take that time series and then regress it on sea surface height in the rest of the model, we can see that this does in fact give us a common mode of variability along the US East Coast. We can use this same sort of behavior to look at relationships with sea surface height or other ocean quantities or forcing in other locations that might be related to or driving this decadal mode. But what I just wanted to highlight today is that you can also do something where you look at the regression of different fields on that sort of envelope function or that multi-decadal variability, which gives you a sense for what physics might be or what elements might be underlying those periods of enhanced and damped variability. So if we take that modulation time series and regress it on SSH from the model, what you see is a cold subpolar gyre. Well, not a cold subpolar gyre. Low SSH in the subpolar gyre, which might correspond to temperature, could also correspond to a spin-up, which seems to say that this enhanced variability or the damp variability only occurs under certain conditions in the subpolar gyre. There's definitely more to look into there. Okay, so the final analysis that I'm going to talk about is a little bit less directed at a specific research question raised by the coastal sea level record, but I think it's interesting and useful for multiple audiences. And it's also the thing that I've done the most work on, so there's actually some meat behind it. So this study that I'm going to talk about is really just a comparison of the tide gauge record on a point-wise basis to what we see in a low and a high-resolution ocean model. Again, these are forced ocean models, so we're just looking at it the way in which a difference in the ocean model resolution influences the representation of coastal sea level. And we do that on a point-wise basis where we're comparing the tide gauges to the closest grid point. So what we can see in this image, which harkens back to the first slide, is that there is, like we would expect, substantially more variance in sea surface height in a high-resolution model. And you can see that in the Gulf Stream extension, and you can also see that sort of extension of high variance moving along the U.S. southeast coast, which is an area that's really difficult to represent in a coarse resolution model given the extent of the continental shelf. So it seems like, in this picture that we're getting improvements, and that actually, shows up if we look at this grid point to tide gauge comparison, where the tide gauge is shown in black, the coarse resolution 1 degree model is shown in blue, and the high resolution 0.1 degree model, ocean model, is shown in orange. So you can see that visually the HR amplitude of the variations at these annual and longer timescales is much more comparable to what we see in the tide gauges, and it ends up being better correlated in this particular location as well. So don't have enough time to get into the details of everything that's in this paper, but I'm happy to share a copy with anybody who's interested. But we do these analyses not only with respect to the US East Coast, but also globally. So you can get a sense for the regional variation in the representation of the tide gauge record in a high resolution model and in a low resolution model. And so this figure is showing the normalized increase in the variance between the high resolution and the low resolution run on a log 10 scale. So 0 means there's no difference between the high resolution and low resolution model in terms of the variance. And what you can see is, similar to the results on the slide before, in the southeast US, you have a greatly increased variance. Also in western boundary currents near the Kuroshio, marginal seas. But there also are areas where you don't actually change much of the variability at annual and longer timescales when you go to a high resolution model. You can point to Australia, which came up in the previous example. You see a lot less in the Pacific and in these eastern boundary current regions, a lot less increase in the amplitude of the variability. So there's more there in terms of how these match up with respect to correlations. I just don't have time to talk it through today. Okay, so where is this all going? I'm hoping that as I start to work on these problems, I can also, on the side, work on some diagnostic tools that might help with this comparison. So on the left is an example of what I'm working on with colleagues at AAR and GFDL in the context of the NOAA Model Development Task Force. That project is only focused on looking at mean dynamic sea level, time mean dynamic sea level along the coast, which sounds like it'd be kind of easy, but it's actually not that easy, especially getting uncertainty estimates that are meaningful in terms of comparing the models and the observations. So we have a paper coming out working on that, and of course that's going to be incorporated in the Model Development Task Force diagnostic package. I'm also working on the side, how to incorporate some of these diagnostics from tide gauges and altimetry into that look at variability relative to those products as opposed to the mean state. As of right now, I don't have a great vehicle for that, but I have started my first GitHub repository of Jupyter notebooks. This has been a big learning experience for me over the past year or two. It's called PyGauge, which I think is a pretty cool name, but there's just the start of some of these diagnostics that are available. And I'd like those to span different frequencies, so we can look at the representation of monthly variability as well as long-term trends. So that's more visionary at this point, but I think it would be helpful and might help expand this work. And I'm definitely willing to take advice as to how to distribute these diagnostics or our new algorithms or ways that we can develop them. Okay, so it was kind of a broad talk, but I hope that these points came out. If they didn't, then I'm going to repeat them. In the tide gauge record, we have this non-stationarity. I think it has important implications on our physical understanding and on the reconstructions that we use for climate and sea level, and also predictions. Are we predicting in the same climate state as we've observed over the altimetric record? I think that we've got the two really cool timescales that are evident in the tide gauge record: decadal sea level variability and modulation of that, which might give us different information about how climate has changed over longer timescales. And then I hope that I've convinced you that there are some promising ways, even though this is a difficult problem, to use new simulations to get at some of the unanswered questions that I have and other people in the sea level community have. And with that, I think I do want to send a special thanks out to Ceres, who sponsored me and helped me out with a lot of the practical and scientific considerations for my time in Boulder. My sponsors, Steve and Chris and Antonietta, were super helpful. I don't know if we've gotten solid results yet, but I think over the next time, once I get back home, we'll have a lot of really interesting stuff that got stirred up. Steve and John, I want to thank for their help while I've been here. NOAA, GFDL, and NCAR, all of these simulations wouldn't be possible unless there was a concerted lab-wide effort and the availability of these simulations to use for the science questions that I'm interested in. And then I want to thank funding agencies and all my collaborators as well. Thanks.
Thank you so much. Do we have any questions in the audience? And I forgot to mention, for those people who are watching YouTube stream online, please post your questions through Slido. I hope the Slido channel works today. Okay. Any questions from the audience first? Yeah, Dan.
Thanks a lot, Chris. I'm interested in the non-stationarity piece of it. And I guess first, I was wondering if you could talk a little bit more about the choice of an AR1 as a null hypothesis to test against. I guess it is kind of a short record over which to identify non-stationarity on decadal timescales. Mm-hmm. And then also, the potential mechanism that you talked about with waves propagating and stuff. Would you expect to see the non-stationarity emerging from that the changes in atmospheric forcing are what then propagate to the sea level? And have you seen any evidence for that?
Okay, the first one, AR1. I think in the analysis, I let the decision about what AR model would be best, whether it's 1, 2, 3, to come out of the analysis. I did not test alternate sort of red noise approximations to really determine the significance there, right? So it's worth thinking about, I think, alternate choices there. AR1, of AR models generally was the one that fit okay, that fit best. Okay, so the next question. So in the reanalyses, we did see change in the amplitude of like SSTs and surface pressure variability and winds, right? So I think that's what you were asking in terms of whether we see that non-stationarity in power in other quantities. Whether we can trust those reanalyses, because as you go farther back in time, maybe they're smoothed more, maybe they don't see that. So I think actually that's the delicate thing that I was treading with that paper, right? Is that I want to relate this to climate quantities, but tide gauges might actually be a more stable measurement. So I don't want to weight what I'm seeing in the reanalyses there. Does that make any sense? Okay.
Okay. Ayla, and then over there.
Yeah, I guess you've emphasized the stability of the record. I was just wondering, are there any concerns about changing observing practices that could lead to that jump in the variability when you saw it?
I mean, there are in terms of the datum, they move around sometimes, but they're quality controlled by PSMSL, which I forgot to thank. That's the tide gauge data set, very helpful. Not that I know of. I mean, I am not someone who has gone out and messed with these its tide gauges and understand the measurements. But I think it would be hard to see that sort of systematic shift in so many different locations. But I'm happy to, if people know more about the actual measurements themselves, to think about it.
Okay. Do we have a question over there?
So you use these force simulations. So do you know whether there's as strong decadal sea level variability in the coupled model of CSM or not?
I would like to see that, and I meant to mention that at some point. But yeah, I think it would be. I don't know off the top of my head. Maybe others in the audience do. But I think it would be interesting to apply the metrics that I applied in that first case study to specific decadal variability in the coupled models. I just don't know the answer yet. Do you?
No. Well, I got another question then. Can you go back to the slide with your hypothesis of
yeah.
And explain to me again what creates the 2-year time lag? That one.
All right. So the 2-year time lag between what we're seeing on the West Coast and the East Coast. So I assume everything occurring on the West Coast is very fast, right? Because you've got this Kelvin wave propagation or coastal wave propagation. And then the pressure fields adjust quickly to that SST anomaly. To that Central Pacific SST anomaly. So the idea is that surface forcing results in this case, in the positive phase, reduced heat loss in the Labrador Sea. And then that changes the water mass properties, and it's an effective signal that propagates along the coastline in the slope current or the deep western boundary current. And so all this atmospheric stuff happens rapidly, but then there's a lag driven by that sort of advective ocean signal in this hypothesized framework.
You're assuming that the ocean coastal waves are very fast on the West Coast, but take a year or so on the East Coast. So what's the difference?
Well, I was thinking that it's not necessarily coastal wave propagation, but it's more of a an advection of that water mass anomaly along the coastline rather than wave propagation on the East Coast. Also but the combination of wave versus advective processes, I can't resolve that. I can only kind of hand wave at the lag being indicative of that. It's a good question, though.
Okay. Go, Kat, and then.
Yeah, but I mean, that part, I wasn't going to ask you, but that part gets into hand wavy part of whether Labrador Sea deepwater formation is actually interior path, western boundary path, and it may be longer than 2 years, actually.
let's dig in. And Steve and I have definitely, tried to reconcile, what's happening in coastal sea level with what we're seeing at the larger scale and in the interior. It's complicated, in part because there is some measure of coastal forcing which is happening that's correlated with what's happening as well. So the time lag, I don't know, it could be a mixture of these things that are happening at the coast, which might confuse the interpretation there. We'd have to really perturbation type experiments in order to, I think, get at the relative roles. Anyway, it's a good question. Good thoughts.
Okay.
I'm wondering if the hypothesized mechanism can also explain this sort of disconnect in Europe where you don't see this 12-year power. I'm not an oceanographer, so I don't know, but I feel like does that explanation not propagate to the east as well, toward the European continent?
I mean, I'm not an atmospheric dynamicist, so I don't know exactly how to think about these surface pressure perturbations, and whether this is truly the extent of them. When you look at the coherence plots of surface pressure associated with that sea level variability, there's coherent variability happening in many parts of the, and that's probably the issue with the statistical relationship, is it's tough to parse out what's the causal driver of the sea level variability in that type of analysis. The question is, is there a pressure signal? Somehow it just doesn't translate into sea level variability at that frequency band in Europe, which could be either that there's not atmospheric variability at the frequency band, or it just doesn't sort of hit the drive sea level in these locations. I mean, I guess the large-scale nature of it would sort of indicate that maybe there's not as strong a forcing happening there.
Okay, I actually saw 2 questions online, but we are almost out of time, but let's do a very quick.
And I got 2 weeks.
Okay, yes. Chris will still be here. So you can actually ask questions through email. So this is from Justin Small. Chris, thank you for the very nice talk. Regarding the ratio of variance between high resolution and low resolution, I have also looked at variability of the US West Coast, California current, and find very similar variability in the high and low resolution. I don't fully understand why. So I guess this is more like a comment than a question.
Yeah, let's talk more about it, Justin. I think let's see, they're both damped relative to tide gauges. That's the one thing that comes out of this analysis, is that it's not that the LR's right, it's that they're both damped. So actually in that paper that's coming out eventually, or being reviewed, we have some, we look at large scale sea level variability and find that it's actually damped all through the tropics. This is actually an interesting result. Maybe I should have shared it. That sea level variability at these longer than annual timescales is damped in both the HR and the LR in these forced cases. And so if that's damped, then potentially, it's more of a large scale thing that's going on in the models than something that's trapped to the coast, which I think is an important aspect of that analysis, is that, sometimes there's a lot of improvement driven by representation of coastal processes, and sometimes it has more to do with large-scale sea level climate variability.
Okay, so the last question from Yuan Pu is the effect of moon included in the dynamical tide model?
So, I mean, in general, and people at NCAR can talk to me more about this, but I don't think tides are usually included in these global climate simulations. But they're probably parameterized in terms of mixing and stuff. So yes, the movement of the moon in reality does modulate tides, but its effect is not in the model, and I can't really speculate how that would affect sea level over these longer timescales.
Okay, this is the top of the hour. Let's thank Chris again for the wonderful talk, and thank you so much for attending today. Thank you. And if you have other questions, please email Chris or just talk to him.
Yeah, please.